Hi guys. So we got to talk about some methods here, and this is the tools. This corresponds to chapter 20 in the Walton book. You can also take a look at the Walton book, and you'll see various examples that Deming presents via Walton for each of these ideas here. The idea of doing it with data, as you can see the subtitle here, is explore, discover, or understand. Other people say this is a great way to convert opinion to fact. I'm not crazy about that statement on the basis of some technicalities. That is, let's begin to support opinion with evidence might be a better way to get at that. But what do we know? Well, we convert opinions to evidence-supported understanding or knowledge. When we use data, we can better understand the systems in which we're operating or the systems in which we're embedded. It allows folks to organize their thinking about the process and systems and make better choices. It demonstrates continuous improvement. Okay, and that's hugely important. If you want to go on a diet, you're probably going to implement some system of measurement to verify that the diet is working. So you may be a scale lover and you want to get on there and you're going to look at the pounds, perhaps the ounces, right? Maybe it's a measurement-driven thing that you say, man, I really want to get into the size 6. So you'll know when you get there because now the size 6 fits, right? It could be if you're a bodybuilder. That is taking measurements of body parts. You know, you want to have biceps that are like 18.5 inches, so you measure your progress towards that, right? But this is about demonstrating continuous improvement, right? In whatever context, in whatever domain we're discussing. We can use data to select improvement projects and use resources wisely and efficiently. In one total quality recognition day we had, I remember being taken aside in the stairwell at the mill. The president of the company, George Herod, he was part of the group we were touring together, and he grabbed me by the arm and said, "Hey Mark, hold on for a minute, I want to talk to you." And basically, just he and I in the stairwell, he said, "Look, I think the project that you guys did on aligning the 3-hole punch paper was a great project. You guys are the first ones to demonstrate the use of a process capability index applied to one of the processes in all of Boise Cascade. Congratulations and kudos." But he said, "Here is something else I want you to consider. How much money did that project save?" And I said, well, in this case, we were responding to complaints, so we hope to avoid complaints of a similar nature. And he says, how much was that complaint? It was $28,000. And he said, okay. But he said, I think that you guys need to start focusing on projects that are linked to more money. Right. He said, good practice project, but we got to think in terms, we got to start thinking big about dollars. Either saving huge amounts of money or new businesses that will make a lot of money. So how product selection, how process improvement endeavors are selected should be on the basis of data, right? It can point out, data can point out where special causes are producing observed outcomes and or variance. And we're going to look at tools to do that. Identify common cause variation that exists within the system. And Deming's all keyed into this is, did this happen because someone screwed up, or are we just observing normal variance within the system? Right? Let's go to Piaget for a moment. And you say, well, what the hell is Piaget doing here? Well, why not? He had a lot to say about how we process the world cognitively and how we develop those skills in our childhood. Scientific thought, then, is not momentary. It's not a static instance. It's a process. And notice, it's a combination of what we learn in concrete operations and formal operations that allow us to become very effective in problem solving. Now, what can we look at? Well, there's a couple charts that help us on our path. Check sheet. I should have been using, I'm actually retaping this lecture now. I could use a check sheet. I started it, and there's multiple things to do. I got to get the lecture loaded up in the proper position. I got to get the iPad charged and ready to control the camera. I got to have a blank memory card in the camera, fresh battery in the camera, right? What did I forget to do that I had to re-record this part? I forgot to turn on, I forgot to turn on the microphone, so there was no sound. and it really pisses me off, right? To, let's say, do 20 minutes worth of videotaping and have to just shit can it because, and see, that's where a checklist shines, because you check off each part of the process. Of course, how would you know what the parts of the process are? Probably because you did a flow chart, which is the last point on here. Now, run charts just allow us to track data over time. So a run chart that we're probably getting pretty familiar and seeing is how many cases of COVID per day, right? And that's just, we plot a point, and that allows us to calculate an average over time, and then we can see, was this day above average in the number of cases or below average, right? Now, the control chart gives us a little more information, because now that we have, let's say, 100 days of COVID information, we can say, okay, on those 100 data points, let's calculate a mean, and then from that mean, we can calculate standard deviations. And that allows us to know, is this kind of an expected outcome? Is it within one standard deviation of the mean? Then we would probably expect that level of variance. But if it's like 3 standard deviations out of the mean, we say, what the hell happened on that day? So it allows us to then use a system to predict the system's own future behavior. What else we got? Histogram. We're familiar with those. Teachers love to use histograms, you know, to look at, for example, grade frequencies. Pareto charts we've already experimented with, as you saw. Scatter diagram. Test the relationship between 2 variables. Cause and effect diagram. Let me get to that here in a little bit, and then systems model and flow charts will wind it up with that. Now, other techniques that are associated to this, right? Brainstorming and 10-4 voting. So let's consider those. Remember, this is a way that we generate opinions, so we'll take a look at how those fit in. I'm not going to go over the instructions of brainstorming or 10-4 voting again. You guys have already had an assignment on that. Let's jump forward to Kuru Ishikawa. Kuru Ishikawa, right? He wrote the Guide to Quality Control in 1986. He's worked with Deming and done a lot for us to understand how to apply the tools to a context of quality control within organizations. Right? So the cause and effect diagram, and one of the most important, is typically used post-brainstorming, but can use to record brainstorming ideas as well. So, and an example that Ishikawa gives in his book is, let's consider that we're seeing burnt cookies in our cookie baking factory. And it's getting to the point where it's a problem. We have to throw the burnt cookies away. Notice there's nothing you can do with a burnt cookie. Once a cookie's burnt, it really becomes trash at that point, and represents a huge expense. Too much cookie burning, and our cookie company is simply going to go out of business. So Kuru Ishikawa gets us all together, and we go, hey, what are the possible causes of burnt cookies? And we brainstorm a list of possible causes of burnt cookies. The cause and effect diagram is how we're going to then array them for visual display, right? And we often then take the causes, the classes of causes, according to criteria, and Ishikawa suggests some ready-made criteria, but we can deviate and make our own depending on the nature of our problem. And he says, in the cookie factory, we have materials, right, like dough, etc. We have methods, the way we do things. We have manpower, that's what the people and how they involve themselves, and we have machines. We can array, or we can assign the different causes to these different kind of conditions. Right? Now, what's the point of all this? Because it kind of focuses and facilitates discussion, greater awareness of the process and system, especially when we make it visual and we're all looking at the same thing. The complexity of the diagram often indicates how complex the process is. It can serve as a guide to what needs to be learned, what data needs to be collected. So we might say, well, there seems to be a huge amount of variability. I think variability in the oven temperatures is causing the problem. And we say, well, how can we know that? And then we can design an experiment to test and measure, right, the oven temperature variability to see if it in fact is an issue or not. So it allows us to either test issues or eliminate issues through the process of experimentation. It involves participants in the process to a greater degree, and people tend to like this and get pretty wound up about doing it. Okay? It's also known as fishboning, and you'll see on the basis of the diagram why it's called that. Now, Kuru Ishikawa cautions us that often ultimate causes, root causes as he calls them, can be 5 times deep. And what this means is we have to ask the question, well, why are the cookies burnt? And they say, well, perhaps the oven temperature is fluctuating. And then we say, well, why is the oven temperature fluctuating? Well, it could be a manufacturing defect in the thermostat for the oven that allows too much variability. Why is there a manufacturing defect in that? And notice that then eventually we get down to some kind of root cause, and that's what we really need to address to make things happen. So 5 times deep, it's kind of like the kids. You know, and I know most of you don't have children, but sooner or later, if you get children, you're going to have to play this, so irritating game. And they're going to say, Mommy, why does... And then you tell them the answer, and they say, well, why is that? And then you answer that question, and they say, well, why is that? Right? And 5 times deep. Notice, children are kind of a natural for this. So this is something that just facilitates the process. Note, we state a problem. We brainstorm a list of possible causes to the problem, and then we assign them to the fishbone. Notice, there's the head. Here's the backbone. It's the fishbone. So, some causes are going to be related to equipment, and they'd be placed in these areas. Some are going to be related to processes. Some people, management, environment, materials. Note, flexible application of the number of radiating bones. For example, here's a different kind of example. Product failure. Well, what we find is some people say the product failure occurred lack of buy-in. So we say why, right? And we list those here. Other people suggest that increased cost by greater than 80%. Well, why, right? Quality issues not identified. Well, why? Right? Unclear requirements. Well, why? So we learn about what went wrong, but by learning about what went wrong, maybe that we can then limit the extent of malfeasance in the future, right? So, any guys photographers, you know, if you're looking at your pictures and say, shit, I got a lot of blurry photos, you might ask, why do I have these blurry photos? And if you belong to a camera club, right, you might toss the question, why are my photos blurry? Or you might be on a discussion board on the internet, why are my photos blurry? And they say, well, you know, there's a bunch of possibilities. You might have a dirty lens. Clean the lens, right? You might have the wrong lens on there. You might have set the wrong exposure. It might have been out of focus in the first place, right? Subject might have been moving too fast. You didn't use a high enough shutter speed to stop it. So in this way, we learn and we explore. Notice the impact of Ishikawa is international. Here's a French version of how to, in fact, use the fishbone diagram. No shortage of versions across the world. Ishikawa is one of those people that will never be appreciated to the extent that he's contributed. A lot like Deming. Right? These are kind of quiet guys, you know. You see them in their suits and ties. They're very technical, and they're easy to ignore, but they're profound in their thinking. And here's from Ishikawa. As much as 95% of quality-related problems in the factory can be solved with 7 fundamental quantitative tools. And this is what he's urging us to do. Now, based on this strange semester, we do a cause and effect diagram assignment in class. But since we're not in class, I kind of thought, you know, I don't think it's going to be appropriate to do it. But now I've second thought myself. So here's the deal. I'd already mentioned we're going to have an extra credit opportunity, and that is to rewrite or redo an assignment. But I thought for this class, I'm going to give you an option. So you'll have 2 choices for extra credit. Now, you can always do one or the other, not both. So please don't even ask, right? But you can either do, hey, let's rewrite an assignment, that is, improve an assignment, and this is as a team, right? Or you can choose to take on this assignment, which is to generate a cause and effect diagram. And I'll write this up. I haven't gotten it written up yet. But so the starting point is poor grade on an exam. That's the problem. Then you ask, what are the possible causes of a poor grade on an exam? That's the brainstorming portion, right? And once you get your brainstormed list of possible causes for a poor grade on an exam, then you put them on the fishbone, right? And then you're going to have your radiating lines, which are major categories, and then you're going to fit all those possible causes onto this, okay? And this could be produced in PowerPoint or Word easily enough. They both have arrow line and arrow drawing tools, so that would work in text box tools. So you could do that. PowerPoint would probably be pretty easy to do it. Or you might find software out on the internet. Questions about that? And like I said, I'll get you an assignment written up on that, but that will be something you can do. That way, if you're interested, you can, and if not, okay? So, B.F. Skinner comes along and he says, hey, regard no practice as immutable, change and be ready to change again, accept no eternal verity. There is no absolute truth, right? Experiment. Try out different things and see what works. And it's having that kind of attitude to adapt, to change, to experiment, to explore. If the organization is driven out fear, then we're free to explore, adapt, and change. And that's, so important to Deming's 8th point, if I remember it correctly. Okay. Run charts, what do we know? Okay, they demonstrate the measurement over time, as we talked about. I explained in terms of COVID, we can do it on a daily basis. And then based on watching the fluctuations, then we can calculate the mean, and that can be the center line. If the process is in control, we can expect about half the data points above the mean, about half the data points below the mean. And then we can go ahead and move on to control charts, where we apply the generated standard deviation lines as well. So now what we have is if the points are within the control limits, then we can say, hey, this is what would be expected. This is like normal variation. If we see major differences, then we got to get suspicious. We have to wonder what's going on with the process, and we have to explore more deeply. Histograms. Let us not belabor it. Demonstrate the frequency of measurements. Typically, each bar represents a range of continuous measurements. So if we look at grades, there'll be a bar that represents a frequency of students achieving an A on an exam or in the class. But note, within that bar, that A bar, it really represents percentages from 93 to 100%. The A minus bar then would represent 90 to 92%, right? So they convey information that's similar to a frequency distribution, the curve that we might see displaying the range of IQs from an IQ test, and they often have the curve overlaid, but not necessarily. Now, you've already done a Pareto diagram for this course, and Villafredo-Pareto observed that 80-20 rule. Notice this is similar to Deming's 85-15 rule, right? And Pareto charts can be used in conjunction with the fishbone diagram, and that is the top 2 or 3 causes are usually responsible for about 80% of the defects. Now, let's talk about scatter diagrams very briefly. What we're talking about here is assessing the relationship between 2 variables. Right? And there's a lot of different ways to kind of operationalize variables and look at variables, but ultimately, if we need to know there's a relationship, we're going to, in fact, use a scatter diagram. And we're going to use a diagram, and I'm going to hit on this pretty hard. We know that correlation is not causation, so it just merely shows an association or relationship. It can demonstrate the direction of the relationship as positive or negative, right? It can demonstrate the strength of the relationship, and that's why we use scatter diagrams. It's got to be interpreted visually. And Dr. Newcomb, I had him for a 3-quarter stat sequence at UCI. It was a horrible bitch of a class. I mean, it was very useful, but it was very, very hard. All of us took it pass-fail, because Newcomb had a reputation for not giving any A's whatsoever, and in our semester, in our quarters, true to form. I pity the poor woman who said, no, I'm going to take it for a grade. She had a 4.0 going in this class. She took it for a grade, and he gave her an A minus. Yeah. The rest of us said, we told you, sorry, but don't take it. Don't take it for a letter grade. Take it pass-fail. Right? I would have had about a B minus in the class. Yeah, it was horrible. But he said you got to interpret scatter diagrams visually. He says if you just look at an R number, if you just look at the output from, let's say, Systat or whatever program you're using, right, and try to calculate it numerically, you're missing something. Because these 4 scatograms represented by Anscombe's quartet, statistician Anscombe developed these. All of these have the same R value, and they all have the same regression line. And this is crazy because if you look at these 4 data sets, they're dramatically different. This is a typical data set. And notice, it conforms. We have a regression line. We have about equal number of points above and below, right? So I'm looking at this process, and notice I can also say, it looks like it might be in control. Run chart would be better for that, but it does the same thing, right? Now, notice this one down here. This is a typical. This one has the same R value, 0.82, high correlation, but notice, there's an outlier that's driving the effect. Okay. In this case, we have a curvilinear relationship, so all bets are off. We don't even know what the hell's going on here on the basis of an R value. It would hide the fact that it's curvilinear. Right? And then this last data set is wacky, right? And this demonstrates a severe restriction of range, but that would be hidden if we just looked at the number. So, as Newcomb admonished, frickin' gotta look at the diagram, right? Not just the numbers. Okay. So thank you, Dr. Newcomb, for that. One thing about Dr. Newcomb, man was super meticulous, and it was hard not to respect the guy. He'd been president of the American Statistical Association, etc. But kind of trivia background factor on him. He was an aircraft carrier pilot in World War II, and boy, that is some scary stuff when you think about it. Especially, I can't even imagine trying to land a plane on an aircraft carrier at night in 1944. Oh my God, so amazing man. Let us then go to part 2 and